Okay. Hello everyone. Welcome to the problem solving session week 3. So in the last week we saw the model called non-deterministic finite automata, and we compared it with right. So we saw this model called non-deterministic finite automata, and we saw that this is equal in power to a DFA. So if you have an NFA for some language, you can always convert it into corresponding DFA. And let's recall what is a NFA model. So you have this 5 tuple Q, sigma, delta, Q0 and F, where Q0 is where Q is the set of states, then sigma is your alphabet, delta is the transition function, which is defined as a function from Q cross sigma to the power set of Q. Q0 is the start state, and F, which is a subset of Q, is the set of final states. Right. So we saw that NFAs are a generalization of DFAs, and we compared the power of So we compared the power of NFAs and DFAs. Right. So in this week we're going to look at a different model which is called epsilon-NFA. So epsilon-NFAs are slight modifications of it's a slightly differently defined variant of your NFAs. So how do we define an epsilon-NFA? It is defined as the set of 5 tuple again. Okay, and the only difference with respect as compared to the NFAs is that your delta now has epsilon transitions. So what that means is in case of NFAs, you could have transitions like 0 goes to say Q1, 0 goes to Q0, and so on. You could have multiple transitions on the same symbol. This was allowed. Okay. Now in case of NFAs, epsilon-NFAs, there is one more additional feature. What's the feature? You are allowed to make epsilon transition to some state. So for example, if you for example, this is an epsilon-NFA because on Q0, when you see an epsilon, you go to the state Q1. Now let's see how this epsilon-NFA reads a string. So for let's say you want to read x equals a. So how does this proceed? You start with Q0, which is your initial state. Hi, I'm audible, right? Okay, so so we were recalling this definition of epsilon-NFA, and how is this defined? You have a 5 tuple, which is the set of states. You have alphabet, you have a transition function, then you have a start state and F. Now, how is this different from an NFA? Your epsilon-NFA has this additional transition on an epsilon. So for example, here, if you are at Q0, you can reach Q1 on reading an epsilon. Okay, so let's start by reading a simple string x equals a. So initially you are at Q0 because that is your start state. Then if you read epsilon, you go to state Q1, and if you read a, you go to Q2. So on reading a, you reach a final state. So a will be accepted. And just to recall, when we say epsilon, it's an empty string. So epsilon A followed by epsilon is same as epsilon. Or if you read two epsilons concatenated with A, that is also same as A. So it doesn't matter how many epsilons you read before or after. You're basically only reading the symbols in this. So just to be clear, let me take one more example. Epsilon A, epsilon B, epsilon. This is same as AB because epsilon is an empty string. So, okay. If there are any doubts, please feel free to ask. Okay. So yeah, so that was a quick recall of what is an epsilon-NFA and how it reads a string. So if that is clear, let's start with a simple example. Sorry. Yeah, let's start with a simple example. So you're given an epsilon-NFA and you want to draw the computation tree on the string x equals BA BBA and you want to check whether it is accepted. So what we did over here in this example was we drew this computation tree for A. So maybe let's take one small example. Uh, I'll draw the computation tree corresponding to x equals BAA. Then I'll give you some time to solve the problem for BA BBA. So let's see how this works. So initially you are at Q1 because that is your initial state. Maybe, okay, I'll start here. Okay, so initially you are at Q1 because that is your initial state. Then let's say you read epsilon. So what is the transition on epsilon? From Q1 you go to Q2 on reading epsilon. So what you do is on epsilon you make a transition to Q2. Okay, now on Q2 there are no further epsilon transitions, so we will not make further transitions. What we'll do is now we will read the first letter of the string, which is B. So if you are at Q2 and you see a B, you basically end up at B, or there is this other transition on B which takes you to Q3. So like, sorry, right. So like, yeah, just like your NFAs, your epsilon NFAs also have this property that you can branch out to multiple states if you read a symbol. So, right. So on Q2, if you see a B, there are two possibilities. Either you stay at Q2 or you go to Q3. Okay. I hope this was clear. If not, please ask. Okay. Now, every time you reach a new set of states, what you do is you ask again, are there any epsilon transitions? So at Q2, there is no epsilon transition here. There is nothing that takes you somewhere else if you are at Q2. Similarly, look at Q3. There is no epsilon transition. So maybe what I'll do is I will just draw the transition table so that things are clear. So you are at Q1, Q2, Q3, and the symbols are AB. Okay. So if you are at Q1 and you see epsilon, you go to Q2. Okay. If you are at Q1 and you see an A, there is no transition. If you are at Q1 and you see a B, again there is no transition. Okay, sorry about that. This is Q2 and Q3. I missed. Just to make it clear, there are two transitions on epsilon. One that takes you to Q2 and the other that takes you to Q3. So okay, I had missed it out earlier. I hope there is no confusion. If you are at Q2 and you see an epsilon, there is no transition that is defined. So this would be fine. If you are at Q2 and you see a CNA, you go to Q3. And at Q2, if you see a B, you go to Q2 or Q3. And if you are at Q3, you see an epsilon. Again, there is no transition that is defined from Q3 on epsilon. So this would be phi. And from Q3, there is one transition that takes you to Q1 on A. So, right. So on Q3, if you see an A, you go to Q1. And on Q3, again, there is no transition on B. So this would be phi. So let me start by redrawing the computation tree now. Okay. Okay. So what you do is, initially you are at Q1. If you see an epsilon, which is this entry, if you are at Q1 and you see an epsilon, then these are the states that you reach. So you can reach Q2 or you can reach Q3. Again, you ask the same question. Are there any states that you can reach from Q2 if you read epsilon? There is nothing that you have further. So you won't extend this. You'll stop there for Q2. You look at Q3 and ask the same question. Is there any transition on epsilon that takes you to a new state? No. So you don't need to again add transitions for epsilon. Now what you do is you read this B. So on reading a B, from Q2, which is this entry of the table, it takes you to Q2, Q3. So we will add the transition Q2, Q3. Okay. Similarly, if you are at Q3 and you read a B, it doesn't take you anywhere. So what you will do is just similar to your NFAs, since there is no transition, we will stop the exploration for this branch, and we will continue with the rest of the branch because there are still elements. Okay, so now what you have done is we have read one alphabet of your string. Now again you do the epsilon closure. So is it that if you are at Q2 and which is here, and you see an epsilon, do you basically get any new state? No. Similarly for Q3, if you are at Q3 and you see an epsilon, there is nothing new that you get. So what do? You read the second letter of your string, which is A. So on Q2, if you read an A, which is this entry, you get a Q3. And from Q3, if you read an A, then you get this entry, which is Q1. So far we have read two letters and the only thing we are left to read is A. But again we will do the epsilon transitions if there are any. So let's look at Q3. There are no epsilon transitions on epsilon, so we don't do anything. But on Q1 there is an epsilon transition, which is to Q2, Q3. So you will add two more states now, Q2, Q3. Okay, so yeah. And again, if at Q2 you don't get anything new by looking at epsilon, so we are done looking at epsilon. Now we will read this third letter of our string, which is A. So if you are at Q3 and you see an A, then you go to Q1. Sorry. Then you go to Q1. If you are at Q2 and you see an A, you go to Q3. And if you are at Q3 and you see an A, then you go to Q1. Okay, and one more time we're going to do the epsilon closure. Why is that? Because we know that BAA is same as BA epsilon. So you're going to account for these epsilons as well in the epsilon transition. So we're done reading this. What we'll do is we'll read the epsilon now. So if you are at Q1 and you see an epsilon, then it takes you to Q2, Q3. And yeah, and that's it. So you get all these states, all the set of states that are reachable from Q1 on reading BA are Q1, Q2, Q3. So since it contains the final state, which is Q1, so Q1 is in the set of final state, so you would end up accepting BA. Now if you try to do the same thing for okay, let me try to get this on the other page. Now if you try to do the same thing for BA, BBA, let's see what happens. You are at Q1, then you see epsilon. It takes you to Q2, Q3. So your string is BA, BBA. Then you see the CB. So Q2 takes you to Q2, Q3. If you are at Q3 and you see, yeah, just to connect you, Tanmay, so what we're doing is we have this epsilon-NFA, and we are trying to draw the computation tree for this string x equals BA, BBA, and we're going to check based on that whether it's accepted or not. So far we started with Q1, and on epsilon transitions we got these two states because epsilon takes you to Q2 and Q3. Then we read the first letter B, and Q2 gives you Q2 comma Q3, and Q3 doesn't have a transition on B, so you would stop this exploration for this branch. Now again you do again you try to do the epsilon transitions for Q2 and Q3, but on Q2 and Q3 there are no transitions that are defined on epsilon, so it won't take you any new state. So you start reading A. So at Q2 if you see an A, you go to Q3. At Q3 if you see an A, you go to Q1. Okay. So let me because I mean if I scroll down, this diagram would not be visible for you. So get let me get this part on over here, and I'll continue from there. So there was some tree over here. You had Q2, you had Q3. On seeing A, you got Q3 and Q1. Now if you read epsilon, then Q1 takes you to Q2 comma Q3, whereas there is no transition on Q3 for epsilon. So yeah, so you stay at Q3. Now you start by reading the third letter, which is B. So at Q3 there is no transition for B, so you would again stop exploring this branch. But Q2 takes you to Q2 comma Q3 on B. And similarly, this branch will also get pruned because there is no transition from Q3 to on B. So what we've done is, so far we have read 3 letters of the string, and we are in this set of states Q2 comma Q3. Now again you do the same thing. Check if there are any transitions on epsilon. But like we saw earlier, on Q2 and Q3 there are no transitions defined for epsilon, so you stay there. Now you read B. So Q2 again takes you to Q2 comma Q3, and Q3 has no transition, so again you stop exploring on this branch. Now you are again in the same loop. Q2 and Q3 both don't have any epsilon transition, so you stay there. Now you finally read this string, this letter A. So Q2, where does it take you on reading A? It takes you to Q3. And where does Q3 take you? Q3 takes you to Q1. Okay. Now, yeah. Now, if you are at Q1, you have already reached the final states, and you have read the entire string. So there is one state among the set of states that you have which is final. So Q1, the set of states, okay, so among this set of states, Q1 is a final state, which is enough. If one of the states that you are able to reach is final, then you end up accepting. So BA, BBA would be accepted by the automaton. Are there any questions? Please feel free to ask. Okay, thank you. So Next, we look at this question. So you have been given epsilon NFA in the form of this transition table, and what are the final states? Q3 is the final state, and A is the alphabet. Delta is given by this table. What this question asks you is, what is the minimum length of string that is accepted by this NFA? So and your options are 0, 1, 2, or 3. So I'll pause for 2 minutes, and I'll let you think. So please share your answer once you're done.
One.
Correct. Abdul, do you have any, what is your guess? You can also use the chat messages if you can't unmute for some reason. Okay. So Tanmay, what is the string that you got?
A.
Correct. Good. So I'll just quickly go over the solution. So let's draw the epsilon NFA. What does it look like? So your start state is Q0 because it is, it is defined here. This is your start state and this is your final state. So Q0 is the start state. On epsilon, it goes to Q1. On A, there is no transition. Q1 on epsilon goes to Q2, and Q2 on A has no transition again. Q2 on seeing A stays at Q2 or goes to Q3. And on Q3, there are no transitions, but Q3 is the final state. So, so if you start at Q0, then the only way you can move is because ultimately you want to reach Q3 in order to accept a string. So you have to move ahead. So the only way to go ahead is by reading epsilon. You get to Q2, then again you read epsilon and go to Q2. And while you can read a bunch of A's here, you can just read one A and get to Q3. So if you read one A, you go to Q3. So what is this is a follow-up question. What is the language accepted by this epsilon NFA?
A plus.
Correct. So the language of this NFA, if I call this N, is A plus, and the smallest string in this set is A, which is of length 1. So the correct answer is B. Okay, good. So yeah, now look at this question. Okay, you have been given this epsilon NFA, and on reading this input 0, 0, you want to tell what are all the states that are reachable. So again, I'll wait for 1 or 2 minutes, and you can tell me your answers.
Miss, what does set of reachable states mean? Can you explain?
Okay, so
Like it is the path.
no. So ultimately, when you are done reading the reading the string, what is the end? I mean, what is the end set of states that you can read? So, for example, when we drew this computation tree, at the end, you own. Okay, I don't know why this is not working. Okay, the charge is gone. Okay, so just a minute. Okay, my Apple Pencil is charging, so I think.
Sure.
Yeah. Okay, so these are the states that you could reach ultimately after reading the entire string. So these are the reachable states. The intermediate ones won't be counted as reachable states. At the end, wherever you can reach. Is that fine?
Okay.
Okay.
This one. First option.
So first option.
Yes.
Okay. Okay. Let's see. Okay. So yeah, you are at you start at okay you start at A. Then if you sorry if you see epsilon, you can go to B or you can go to F. Okay. Then if you read two F's here, sorry, two zeros here itself, then uh, I mean, let's say 00, then you go to, then you stay at F. Okay, so now from F, whatever you can reach on reading epsilon would still be reachable. So let's say, um, okay, let's say you are at F and you have already seen 00. So F is definitely reachable. What is also reachable is E because from F you can go to E just by reading epsilon. So E is also reachable. Now you can reach E by just reading 00. If you again see an epsilon, you go to C. So C is also reachable just by reading 00. And from C, again if you see an epsilon, you can go to B. So you have still just read 00, but you B is still reachable. So you can also go to B. Now, yeah. Now let's explore this other path. So this is your other path. You saw B by reading epsilon. Again, on reading an epsilon, you can go to C.
Ma'am, we can reach D also, no? For the first.
Correct, exactly.
If
So
we
that is from this path, the other path. If you directly go to F, you can't reach B, or can you?
D D.
No. You
It is
can't reach
epsilon, no? C D.
D, right?
It is epsilon, so we can reach, no?
Uh, oh, okay, okay. Sorry. Okay, you're talking about this path from E to C to D.
Yes.
Okay, correct. Yeah. That is also possible, or you can see epsilon, epsilon, epsilon from A to B to C to D. That is also there. So you're right. So D is also reachable. So yeah, these are the states that you can reach. Okay. This is clear, right? Okay. Thanks. So we'll move on to the next question. Um, yeah. So you have been given this epsilon NFA and you are asked what is the complement of this language. So just to remind you, what is complement of a language? L is set of all strings in sigma star such that X is not in L. So if you think of sigma star as all possible strings and L is a subset here, then everything here is L bar. So this shaded region is L bar. So you're asked what is the complement language? So yeah, I'll wait for the
Epsilon,
epsilon.
epsilon. Because A we can reach there.
Correct. Okay, just a minute. Okay, let me see. So the language of this uh,
It
of
would
the
be A
given
plus.
NFA is A plus.
So its complement would be
A
epsilon.
comma epsilon. So the complement of that would be A comma epsilon, right?
Miss, but A it is A plus now, so A will be there in
Oh,
language.
sorry. Yeah, sorry about. Yeah, so that would be epsilon. Correct. So the answer is C. And just to tweak the question a little bit, let's say that B is not the final state, but C is the final state. What would that language be?
Can you repeat?
Yeah, so C is the final state. I'm just tweaking the question a little bit. B is a non-final state. Or let's say that all the final states here are non-final now and the non-final ones are final. So your NFA looks like this. A, B, epsilon, C, epsilon. So we have just swapped all the final and non-final states. So I'm asking you what is the language of um, this NFA now?
It would be 5.
It would be five. Can you think again? Is A accepted?
Yes, because it is a final. If it is A is a final state, so zero length string is included at epsilon,
So that would
and
be A
it forms
star.
a
So that would be A star, right? You're right. Okay.
A star.
A
So
star.
epsilon is included, so it would be 5
Okay, you're
as its
telling me the
complement.
complement. Okay. Okay. I thought you were telling
Uh,
me the language of this. Okay.
no, language is A star.
Yeah, correct. Okay. Good. So let's go to the next question. So, okay. So you have the following statements. Statement 1 is that if all the states of an NFA are accepting states, then the language is sigma star. Statement 2 says that there is a regular language A such that for every language B, the intersection is regular language. So the question asks, I'm asking you which of the following options is correct. So option A is that only one is true. Option B is that both one and two are false. Option C is that only two is true, and D is that both are true. So I'll wait for some time.
Option D.
Okay. Okay, let's see. Okay, so what is your argument, by the way?
Like in the first statement, is it is given key all states are accepting states. So that means all states are reachable in the NFA, right?
Okay, there is a difference between state being accepting and state being reachable. So it is possible that your automaton looks like this. NFA looks like this. A, B, whatever. So all the states are final, but it's not all the states are not reachable. So in this case, for example, the language would be empty.
But it is already accepted states, no? So
Yeah,
this
accepting state simply means final states, as in
okay.
okay, okay. So and what about statement two? Why do you think it is true?
No, no, then the logic will be different.
Sorry, can you repeat again? I couldn't hear.
No, like I first in the before I thought that if all states are reachable, then all the languages will be possible now for that NFA.
You're talking about statement 1, is it?
No, from statement one, I thought that
Oh, okay,
in
okay,
the
okay.
beginning,
Okay, got it, got
I
it.
thought that all states are reachable, so they all things will be possible now. That was my logic for statement two.
Okay, okay, okay. But for statement 1, you agree now that 1 is false. Okay, let me know if not. So my claim is that, I'm saying that statement 1 is false because here is an NFA where every state is a final state or an accepting state, but the language of this NFA is empty. So that is my counter example. And about statement 2, so let me ask you, is the language P regular?
And can you repeat?
So I'm asking you, is the language L equals P regular? Am I audible?
Yes, yes.
Yeah,
Uh,
because
it would not be regular.
sorry, I couldn't hear you.
It would not be regular.
Why is that? So, you can simply have a TFA like this, which, okay, an NFA like this, which doesn't really have any transitions. So the language would be, or let's
Okay.
say that you have a DFA, but no state is accepting. So no matter how you make the transition, since there is no final state, the language would be empty. So since you can give a DFA or an NFA for that language, the language is regular.
Okay.
Okay.
Understood.
So what I'm saying is for statement 2, you take A to be phi. Okay. Then no matter what B is, for all languages B, A intersection B would still be empty. Right?
Yes.
So A intersection would be regular. So statement 2 is true, and how do you get that? You take A to be empty, then you get every intersection to be empty. So statement 1 is false, but statement 2 is true. So your answer
For
is
statement two, we took assumption and then concluded. For statement two.
no. So actually, what does this say? It says that there is some language A for which this happens. So I'm showing you one such language A for which the statement is true.
Okay.
Okay, good. Okay, so I think yeah, this is relatively easy question, but yeah. So you are given this NFA, epsilon NFA, and you have to identify the language of the epsilon NFA.
Option C.
Option C, yeah, that is correct. So okay, so what you do is if you go along this path, then you end up accepting. Then you end up accepting A plus basically A or B followed by A or B star, which is basically A or B plus. And That means you have read at least one A or at least one B in order to reach Q3, and from Q3, no matter what you read, you're going to stay there. Similarly, if you follow this path, even if you don't read anything, you just read epsilon, go to Q1, read epsilon, come back to come back to Q0 again, and you then see an A or B, then you end up at Q3. So yeah, so this basically doesn't necessarily add anything, and the A's here could also be assumed as A's that are read at the end or something. So yeah, the correct answer is C, that it accepts every string W and it has at least one A or at least one B. Okay, so okay, so now you're given this language, 0 star, 1 star, followed by 0 plus, and you want to construct an epsilon-NFA for this. So yeah, the minimum number of states you'll need for this is 3. So I mean, it's okay even if you end up getting more than 3 states, but the minimum you would need is 3. So okay, what we'll do is you are at.
Can we try?
Sure, sure.
Automata.
Yeah, yeah.
Yes, it is for this one. It there will be minimum will be zero. Like it is zero plus. It is 0 star, 1 star, 0 plus. So the minimum string would be 0
Okay,
for
but
this language.
how do you get the epsilon NFA with only one state? How do you? I will draw it. You tell me. So you are at. Okay.
No, miss, I'm asking.
Okay. Sorry. What is your question?
For this language, the minimum would be
Yeah, yeah. Correct.
like for this language.
The minimum would be 0.
So how would we draw epsilon? So epsilon would not, how it would be epsilon in epsilon? If minimum is 0,
Okay. So how is it epsilon NFA is the question?
yes, epsilon in FA, yes.
Okay. So if the okay, what are the strings that are there in the language? It is 0. It could be 0 0. It could be 1 0. It could be 0 1 0, and so on, right?
Yes.
So if you are at Q0 and you see, yeah, and okay, so what I'm doing is that this Q1 state basically takes care of this loop for zeros for me. So I have a loop at 0, and it's going to make sure that if there is any string of this form, then it will process here. Then on epsilon transition, I go to Q2, and again I have this loop for 1, which takes care of the 1 star part. And then I uh, go to Q3 on seeing a 0, and the rest of, I mean, this loop takes care of the trailing zeros if there are any. So what is the language accepted by this? Okay, sorry, I need to make a final state. Yeah, Q3 is the final state.
Question is the 3 states, no? There are 4 states in this question. Like,
Okay then basically you don't start with Q0, you start at Q1 itself. It,
minimum will be 0, yes.
okay, like you can make an NFA without using epsilon transitions, but okay, I mean, it's just that I'm asking you because in this week you did, you had learned about epsilon-NFAs.
Yes.
Okay, like even if there is no epsilon transition, it would still be called an epsilon NFA because epsilon NFAs are generalizations of NFAs. Like every DFA is an NFA, just like that, every NFA is also an epsilon NFA. So even if you construct a NFA without epsilon transition, that's still okay.
Okay, ma'am.
Okay. So so last week I had this question that I didn't get to, because we were already towards the end of the tutorial, we didn't do the question, so let me write it here. Okay, so let's say that L is a regular language and we define LR to be the reversal of L. What do we mean by that? If L is like, let's say, apple, banana, or some strings like that, then what does L reversal look like? It looks at your string and it reverses it, that is, reads it from right to left. So, what does this string look like? It looks like E L P P A. This one looks like A N, if you were reading it backwards, A N A N A B, and so on. So, you get the point, right? So, it basically reads your string in the reverse order. So if x is x1 to xn and x is in L, then x prime, which is equal to xn minus 1, so on up to x2 x1, which is reading the same string in the reverse order, this would belong to the reverse language. So if the definition is clear, the question is LR a regular language? That's the question. So I'll wait for some time.
Yes, it will be.
Okay, so what is your intuition?
Like from the previous problem, you said that if there exists a language where language is phi.
Okay. Okay, then what would the reversal be for that language?
Phi.
Right. Okay. So that is correct. We need to get an we need to build an NFA. So how do you show that some language is regular? Either you give an NFA or DFA or something. So right. So what we will do is we'll try to construct an NFA. Okay, because you can do it with DFAs also, but it's slightly easy to argue with respect to NFAs. So let's say that okay. So let's write the proof. So let's say that L is regular via some NFA, which is N, and N is Q sigma delta Q0 F. Okay, now what I want to do is I want to give another NFA, build another NFA N prime, which is Q sigma delta, or like Q prime sigma prime delta prime F prime, such that the language of this NFA is equal to the reversal. Okay, so So what is the idea? Let's start with a dummy, like some dummy string. Okay. Let's say um, you have some NFA. Okay, there could be other transitions that I'm not writing at the moment. So hi. So okay, let's say that you read the string apple and you reach this final state, say q. So what you want to do is, now you want to read the string in the reverse order. You want to read E, L, P, P, A, and you want to accept. What does that correspond to? That corresponds to Q being your start state and reversing the transition. So if I read E, then I read L, P, P, and A, then I want to accept. Okay. So this is the intuition. There could be like the NFA could be very complicated, but what I want to convey is, if you simply take all your final states. So okay. So what you do is, this is your NFA N, which accepts the language L. So you had some start state, then you had bunch of transitions like this, and you had a set of final states. Okay, so my claim is, for constructing the new machine n prime, you let the states to be, let's say, okay, I'll do it first. Okay, what you do is, you take all these final states here from n and uh, I mean, make them your start state. But you're only allowed to have one start state as by definition. So what you can instead do is, now you can use the idea of epsilon transition. So you add epsilon transitions to all the states and make this your make this your start state. So this is as good as you can start. Maybe I'll name them so that there's no confusion. So maybe this is your final
We
state.
are just reversing the
Exactly.
flow of NFA and changing the start state and
Start
final
state
state.
and final state. Correct. So while it is,
Understood.
yeah, it is obvious that your start state, you can make your start state to be final state, and you would end up accepting it. The only subtle thing you need to do here is that you want all the final states to be start state, but it doesn't allow you to write a set of states to be final state. So what you can instead do is, you just add epsilon transitions to them and make this new state as your start state. Okay, good. So I'll just write it formally. So how do you get n prime? N prime is Q union. Maybe I'll call this new state S. It has one more state, and the alphabet remains the same. We didn't change anything. I will define what is delta now. And yeah, your start state is S, and final state is, let's say in this NFA you had Q sigma delta Q0 F, then your new final state would be Q0, because the start state of this NFA is the final state of n prime. So I hope this is clear. The only thing we need to um, write is delta. So what does delta look like? Delta prime look like, if delta takes Q A to some state P, then delta prime takes P A to state Q, which is reverse of uh, what your previous NFA was doing. So if you were at Q, you see an A, you go to P. Now what we're saying is, if you are at P and you see an A, then you go to Q. That's it. So okay, I hope this makes sense. Okay. So okay, I'll take this question first, and then we'll go. Okay. So I'll read out the question. You have an NFA which has M states, and in the last week you must have seen conversion from NFAs to DFAs, which says that they are equal in power. So you had a subset construction. What this question says is, if you have an equivalent DFA with k states, then what is the relation between m and k? So your options are that k is at least 2 to the m. Option B is that k is at least m. C is that k is at most m square, and D is that k is at most 2 to the m. So take a few minutes and let me know what you think.
Option D.
Okay, good. So why? What is your logic?
Like for NFA, it would be in DFA, like for each and every variable, we can have only one path.
Hmm. Okay.
But in NFA, for one path, we can take all the variables. That is 2 raised to m.
Okay. Yeah.
I took example for binary numbers like 0 and 1.
Okay. Yeah. The idea is right, but if you want to prove it, um, I mean, more formally, then I'll just do it in a few steps. Your idea is correct though. So you saw this subset construction idea, which converts an NFA to an equivalent DFA, such that let me call this N and D, such that the language of N is the same as language of T. So what does it do? It basically makes a transition table like this, and if you are at some state Q and on reading 0, 1, whatever the alphabet is, it looks at all the subsets that you can reach and so on. And the only thing that you do is you treat these subsets as your new states. So each of the subset corresponds to a new state. So there are only, there are only 2 to the q many possible states subsets that you can have. So in this case, q is m. So there are only 2 to the m possible states that your DFA can have. That follows from your idea of subset construction. And your idea is also correct. If you are at some state, the number of states that you can, the possible set of states you can reach is bounded by 2 to the m. So therefore, you have that k is at most 2 to the m. Okay. Okay, and the key, the key word here is minimal. If there were not this, if I write, sorry, the same sentence without the word minimal, then this is no longer true. Okay, why? Can you can you guess why?
DFA is the minimum step, मतलब minimum graph we can say.
Is that necessary? I mean, you could have a lot of dummy states that are not even reachable, and it is still a DFA, right? So, I
But
mean,
it will like consume the variables now. If we take trap states if we create trap state for each state
okay.
in DFA, so like it will be wastage now of variables.
Exactly. It will be wastage, but it is still a valid DFA. It can still accept the same language. So what I'm saying
But it
is,
will increase the number of states now. So
huh,
how then it will
exactly, that's what I'm saying. So if I don't have this condition for minimal and I allow your DFA to be arbitrarily large, then really bound. You can't really say such a bound. Okay.
understood.
That's okay. Good. So yeah. So minimal was a keyword there. Otherwise, you can't say that such a bound exists. But I think yeah, at later point of time, maybe sometime in the course, you will see a step-by-step procedure to convert a DFA into a minimal DFA. So at that time, we'll look into this in more detail. Um, okay. Okay. Sorry. Um, okay. So just to recall, the three models that we've seen so far are DFAs, NFAs, and epsilon-NFAs. And NFAs are generalizations of DFAs, epsilon-NFAs are generalizations of NFAs. And we saw that NFAs have sort of this, by definition, they look a bit more powerful because from one state it allows you to jump to a lot of states. But then we saw by this theorem that DFAs are as powerful as NFAs. Okay, now you looked at this other model called epsilon NFA, where it has somewhat more power than NFA in the sense that you're allowed to have epsilon transitions. That is, you can you can jump to different states without even reading a symbol. So that is the additional feature it has. So again, you might wonder whether epsilon NFAs are more powerful than NFAs. Are there languages such that uh, there is some NFA, some epsilon NFA accepting it, but there is no NFA. So this is sort of the similar flavored question that you had in the NFA versus DFA question. Now you have epsilon NFA versus NFA question. So again, it so happens that your epsilon NFAs are actually as powerful as NFAs only. So if you have an NFA, you can convert it in. If you have an epsilon NFA, you can convert it into an NFA. And the other way around is always true, that every NFA is already an epsilon NFA. So what you know is, given epsilon NFA accepting a language L, there is an equivalent NFA that accepts L. So if you want to directly, if you want to get an epsilon NFA, if you have an epsilon NFA and you want a DFA, you can do the two-step procedure. First, you convert it into NFA. We will see how to do that using by an example. And in the last week, we saw by subset construction how to convert an NFA into a DFA. So if you want to convert epsilon NFA to DFA, you can either go by this two-step procedure or you can use your intuition and combine the two steps at once. So this, I mean, you can do it directly also, but since this part is what we already saw in the last week, what we'll do is we will convert an epsilon NFA into an NFA. Okay, so let's do that. Okay, so you have this simple epsilon NFA. I'll just ask you, what is the language of this automaton?
One star, zero star.
Um,
1 star, 0 star, 0.
okay, but one
Sorry,
is
1 plus 1 0. 0 plus 1 star. Yes.
okay. Good. I see one hand. Saw one hand raised. So is there any question?
No, no.
No, not you. Sorry,
Me.
not you. Somebody else.
Acha.
So okay, I guess not. So yeah, you're right. So the language is okay. No, actually, this is not correct. So what this accepts is 0 followed by any number of ones or 1 followed by any number of zeros. So if you say 0 plus 1 plus, then it doesn't accept, for example, 1, 1 0. Sorry, I couldn't hear you. Can you please write in the messages? Okay, okay, sure. Right. So, okay. So, Tanmay, do you agree that this is the language and not 0 star 1 star?
Yes.
Okay, good. So, like at the end, when we get rid of these epsilon transitions and we convert into an NFA, you can verify that indeed the language of the NFA is 0, is what we really want. So, um, maybe I'll give you 1 minute or 1 or 2 minutes to try to come up with the NFA yourself, and then I mean, we'll discuss the answer.
Okay, ma'am.
Okay. Okay. So, okay, if you need more time, let me know. Otherwise, I'll start.
नहीं मैम नहीं आ रहा.
Okay. So, shall we discuss?
Yes.
Okay. So, okay, so like in case of DFAs, we saw that what was the intuition behind that is you started at some state for NFA and you could reach a bunch of states. Okay, so what we did was we said that we'll replace that bunch of states with a new state itself. That was the whole idea. And then the transition table itself looked like that for a deterministic one. And we modified the panel states and so on accordingly. So what we'll do is we'll appeal to the intuition again. What do we want intuitively is if you are okay, good. So yeah, good. We will see the solution. Okay. Just to ask you, how many states did you get in the NFA?
NFA null to NFA means, ma'am, we'll get all the 6 states, but
Okay.
the null transitions are not there. And as we apply the equation, initial state is also the acceptance state.
Okay. What is your initial state in this in the corresponding NFA?
Corresponding NFA initial state is A.
Okay, so can you tell me what does your NFA look like? I'll maybe draw it. Okay. Is it okay? Can we draw it?
Yes, yes.
Okay. So your initial state is A.
A.
Then
All those 6 states are there, A, B, C, D, E, F.
okay.
A and D are the acceptance state.
Okay.
A and D.
D. Okay.
Dog.
Sorry. Yeah. A and D are the acceptance states. Okay.
Ma'am, B is not acceptance. A initial is acceptance.
Really sorry. Okay, sorry. Yeah. A and D are the acceptance states.
So A to 0 transition will go to C and to D.
C and D. Okay.
A to 1 transition will go to E and F.
E and F. Okay.
B to 0 will go to C and D. B to 1 is to null, so no any transition. C to 0 is null, C to 1 is to C and D.
Okay.
For D, all the null transitions, E to 0, E and F.
E to 0, E and F. Okay.
Again, E to 1 is also E and F.
Okay.
F to 0 null and F to 1 is to E.
Okay.
So this is my NFA. Whether it is correct, ma'am?
Yeah, let me see once because the NFA that I have in mind is slightly different. So let me check once.
Okay.
What is the language? Okay, so in this case, the strings that you are accepting are 0, 0 followed by 1 plus. What are the other strings? Okay, that is all right. Because if I'm right, so from this part, from E and F, there is no way to reach A and there is no way to reach D. So so this part is as if it's not really helping you to get a string accepted. The only strings that are accepted are this 0, or you go to 0 from here and you read a bunch of ones and come back to D. So I think the language of your NFA is this.
Okay.
Okay, but good. I mean, it is quite, quite close to what we wanted. So, so how did you try to get the NFA?
Uh, Ma'am, I referred the book John C. Martin for study of theory of computation.
Okay.
In that, whatever the methods they have given,
Okay.
suppose all the states of epsilon NFA means we'll start with the initial state, and from initial state to zero, how to find it out? First, find out the epsilon closure,
Correct.
then epsilon closure of delta of again epsilon closure of A to zero.
Correct. That is,
So,
yeah, that is the right method. Maybe there was some miscalculation or something. We'll check it. Okay.
okay,
But good for, yeah, thanks.
okay. Thank you, ma'am.
Okay. So, yeah, so we will try to get this and get this epsilon.
Ma'am, for NFA, can we have more than one variables on one path?
Yes, you can.
So it will, for this, can we have 4 states in
Yeah,
NFA?
yeah. Do you have one in mind? Because yeah,
Huh.
the okay,
Initial is A,
okay,
then final is D,
hmm, okay.
then 2 more states B and C.
B and C.
B,
Yeah, B and
B
C.
and C.
Hmm.
Yes, from A to D it will be 0, comma 1.
Okay,
From A to B it will be 0.
okay,
Self loop on B with 1.
okay,
B to D 1.
okay.
A to C 1.
Hmm.
Self loop on C 0.
Hmm.
Then C to D 0.
Okay. Um. Hmm. I think yeah, this works. Hmm. So basically, this part takes care of the 0 1 plus. This part takes care of 1 0 plus, and this is for 0 and 1. That's what.
Yes.
Yeah. So yeah. So you this is correct. What we will do is we'll follow the step-by-step procedure as Anisha was mentioning. So okay. So we will try to obtain the NFA using that procedure. So I'll erase this for now. Okay. Okay. So what you do is you try to get a transition table. So notice that in case of NFAs, there is a single start state from where you go on reading zeros and ones. But in this case, um, yeah, in this case, if you have to read some string, how does the computation tree look like? You would start with A, then you would look at the epsilon. If the epsilon transitions can take you to a lot of states, in this case, it's BF, or you can be at A itself. Okay, now from B and F, there is no new transition. Okay, so if you have read nothing, you are not really at A. You could be at A, you could be at B, or you could be at F, and then you can actually start reading the string that you have. So that is what an NFA would look like. Okay, so what we'll do is we'll try to draw the transition table. Okay, so your start state would, like, I'm using the same idea in case of DFS. Whenever you had a bunch of states, we called it a single state. So this set is going to correspond to some state in our NFA. So let's say this is your state. If you read a 0 and if you read a 1, what are all the possible states that you can reach to? And when you say 0, what we mean is 0 followed by epsilon, or epsilon followed by 0, all possible strings, because they're all equivalent to 0. The only thing you're reading is 0. So that's the intuition. If you are at these possible states and if you see a 0, where all can you land in this epsilon NFA? So let's do that. Okay, what you do is you do the union, you do for individual states, and then you take a union of all the states. Let's say you are at A. Okay, and you see a 0. Where do you go? You go to C. Okay, now you take your epsilon transitions on C. On C, if you see an epsilon, you can either stay at C or you can go to D. So for A, what you got is C comma D. Okay. Okay, okay. And this makes sense, right? From A, you if you read a 0, you can reach C or you can reach D.
Yes.
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 Okay. Now let's do the same thing for B. If you are at B and you see a 0, again on B there is no epsilon transition, so we will not really take that extra step because it will only give you B. If you see a 0, then you go to C, and if you take an epsilon closure now, again you will either end up at C or you would end up at D. That doesn't add anything new. So C and D are already here, so that doesn't add into the set. Now let's look at F. If you are at F and you see a 0, there is no transition. So that branch doesn't add any state. So you get C comma D. Yeah. Now you do the same thing for 1. So can you tell me what should be the entry here?
E comma D.
Okay, good. So you get E comma D. If you are at A and you see a 1, then there is this path that takes you to E, and if you see an epsilon, you can go to D. Now, if you are at B, there is no transition on 1, so this would not give you anything. And if you are at F, it's the same thing again. If you see a 1, you go to E, and on epsilon, you go to D again. So it doesn't add anything. So this is the state you have. So on the left hand side, what we do is you don't enumerate all possible subsets. Why is that? Because if this is your start state and these are the only two states that you can reach, then there's no point in adding transitions for the other states because they're not even reachable. So when do you add a state here? When something new appears here, because only those are the reachable states, so you just need to worry about them. So what we will do is let's take C comma D and add transitions for it. So again, can you tell me what should be the transitions here?
D.
Why is that? Because like on C,
It is null.
yeah, correct. It will be null because
It
uh,
is finance at C comma at CD.
right, there is no
From,
transition.
hmm. From C and D, no any zero transition is there.
Hmm. Correct. There is no zero transition. And what should be the entry for this on 1?
It is CD.
Correct. So it is CD. Now, okay. Um, okay. Now you look at ED. Okay. From ED, where do you go on 0?
ED.
D.
And where do you go on 1?
Null.
Null.
Okay, good. So, okay, let's see whether this gives the same. Okay, let's see. So you are at the state ABF, which is your start state. Then on 0, you go to CD. Okay. On 1, sorry. On 1, you go to ED. Then from CD, if you see a 1, you stay there. If you see a 0 from ED, you stay there. And there are no other transitions. And what should be the final states?
It is only D, madam. CD.
Only CD should be the final state, is what you're saying.
CD and ED.
Yeah, correct. Good. So why is that? Because in the original epsilon NFA, your final state is D. So if at all by any possible transitions along the computation tree, if you can ever reach D, then you would accept. So every set that has D in it should be an accepting state. So so here you have CD and DD that are the accepting state. So what we will do is I'll make this final states. So now we just followed the step-by-step procedure, right? We drew the table and we drew the got an NFA from it. So what is the language of this NFA?
Can you repeat?
So I'm saying from the given epsilon NFA, what we did is we followed step-by-step procedure to get this NFA. And this is clearly an NFA, not an epsilon NFA because there are no epsilon transitions. So my question is, ultimately, if you want to check whether it's correct, your languages should match. So what is the language of this NFA is what I'm asking. This NFA.
Ma'am, I think it is 0 1 star or
Okay.
1 0 star.
Correct. Correct. So note that we at the start we asked the same question for this NFA. This was a language that we got, and now for this NFA we're getting the same language. So that means we the procedure indeed gave us an equivalent NFA accepting the same language.
Ma'am, in NFA, two final states are allowed.
Correct. Yeah. Any number of final states are allowed.
Okay. And in epsilon NFA?
Even in epsilon NF, even in DFA, any number of final states are allowed.
In DFA also?
Yeah. So F is, when you say the 5 tuple, F is a subset of Q. So it could have any number of states.
Okay.
Okay, good. So, so this, I mean, in this case, we did not write every step by step epsilon closure and everything. But I guess in exams and all, you might be expected to write. What I was trying to do, I was trying to convey to you the intuition of why this procedure gives you NFA. So we did not do that step by step procedure for every getting epsilon closure every time because it's a bit it can get messy while explaining, but I think you can practice it. You can look into the lectures how to write step by step, but I hope the intuition was clear. Also, like whenever you do this conversion from epsilon NFA to NFA or NFA to whatever, like whichever way, it's a good idea to always check whether the languages are matching because like some of the times calculation can get off. So just giving you a tip. Okay, so I think we are done with the questions for today, but I'll just give you this is not about, this is not related to your syllabus, but I'm just giving you some interesting information if you're like interested or something. So, okay, so like what we did was you saw this DFA model, you saw an NFA model, you saw an epsilon NFA model. Okay, now there could be like why should people be interested in studying these models only, right? Why was it even defined this way? So it turns out that these are not the first models that came up. Okay, just to give you a disclaimer, like even if what I'm saying right now doesn't make sense, please don't worry because I think it's not related to your, what will be coming up. But I'm just trying to give you intuition about why this was even defined. Okay, so you all know that we, as computer scientists, what we want to do is given a problem, you want to come up with an algorithm and you want a machine to do that. Now, there could be different machines using different softwares, using different ideas altogether. But we want a general sense of when I say a machine, what does it do? So, for that, this model called Turing machines was defined. Okay, you will see this later, probably this model. and I'm not going into the detail of that, but just remember for now that it exactly captures what every algorithm can do. So if you have an algorithm, there is an equivalent machine, and if you have this machine, Turing machine, then you can get an algorithm that way. So anything, any wild algorithm you can imagine has this Turing machine thing. Okay, so these are the models that we had, and uh, okay, and what we this is what came up first, and later on you went on getting simpler and simpler models. Okay, so DFA is probably one of the simplest model that we know, and these are like more intuitive ones, but they end up having the same power. So just like that, there is one more model called 2DFA. So what it does is, um, okay, in case of DFA, you only can go ahead, right? If I have to read A, B, then then yeah, what you do is you start at the state, you go ahead, go ahead. Once you're done reading the string, you decide whether to accept or reject. Now, in 2DFAs, what happens is you're allowed to make backward movements also. So you can read A, B, then you can go back B, A, and so on. So basically, you can move back and forth, but ultimately, at some point, you have to decide whether to accept or not. And it so happens that again, 2DFAs happen to be as powerful as NFAs, or which is as powerful as DFAs. So why people are interested in these models is because when you come across some problems, it is very intuitive to have a model about it, and you want to see where this model really falls, how powerful is it, and so on. So if you are thinking at this point, what are these DFAs, what are these NFAs, and so on, and why do we define it, why do we care? Um, okay, I saw. Okay, sorry. Yeah. So I just want to give you, I mean, just want to tell you that there is a very intuitive reasons why these models were defined, and there is rich history about why it is being defined the way it is. So yeah, I hope like um, I mean, that's all I can say at this point. When we go to more and more powerful models, I think I'll be able to connect you more if you are interested. Okay, so at this point, I just want to say that even if this doesn't make sense, keep it at the back of your mind that there is a very good reason why we define these models. Okay, that's it I wanted to say. And if you have any questions about what we discussed today, yeah, you can stay back and ask me.
Ma'am, do you have some questions for DFA?
Yeah, I do, and it's we had this week one on. I
I
mean,
was not there.
okay, so it is uploaded on YouTube, and
For now, you have. Do you have?
for now, I may not have new questions. I only have those questions that we did last in the week one.
Like, can you
Sure, I can show
create
you.
some? Uh,
Okay. Uh, yeah, this is okay. I can run you through this, but these were like relatively easy questions. You can, yeah. Let me know which one you want to discuss.
no, like, ma'am, like for a given language, we uh, have to construct a DFA. That type
Huh.
of questions.
Okay. Uh,
No, you can like you can randomly create
okay,
for now.
okay, sure. So let me get a page. Okay, so do you have a language in mind, or should I randomly take it?
You can randomly take it.
Okay, so let's say that you want a language that takes at least one zero, or at most two ones. Okay. Okay, I need to construct this. Okay, give me a minute. Or you can also attempt this in the meantime if you want.
Yes, ma'am.
Yeah. Sorry, did you say something?
Ma'am, I constructed one.
Okay. I'll draw it. Okay.
It is with 3 states.
Okay.
Q0,
Okay.
Q1 is the final.
Hmm.
No, Q2 is the final, and below is the Q1. Below.
Below is the Q1. Okay.
Q0 to Q2, it is 0.
Hmm.
Q0 to Q1 is 1.
Okay.
Q1 to Q2 is 1.
Hmm.
Q2 to Q0 is 1.
Q2 to Q0 is 1. Okay.
Q0.
Okay, sorry. Yeah. Here. You.
Self loop on Q2 with 0.
But that would not be a DFA, right? Because you are defining multiple transitions on 0 for Q2.
No, it is Q2 to Q0 is 1.
Oh, okay. Sorry.
Q2 self loop 0 and Q2 self loop 0. Sorry, Q1.
Okay, self loop on 0. That's
Yes.
it. Okay. So what is the language accepted? It is 0 plus or 1 followed by 0 star followed by 1 followed by 0 star. Okay, I think the it covers most of the strings, but I think it doesn't cover the strings of the form 0 star 1 0 star 1 0 star.
Because, like, ma'am, my issue was that there were, for the given language, there is 2 minimum conditions, at least 1 or at most 2. So for 0, it would be minimum 1, on for at most 2, it will be minimum will be 2. So there will be difference in minimum states, no, for this language.
Okay, so basically you are saying that if there were a 0 here, then you would end up accepting because of the first condition. Okay, yeah, that is correct. Good. So, okay, the only thing I can say is, yeah, I think in the first week, whenever we constructed an NFA, a DFA, we did this intuitive sort of thing. Okay, there was no, there was no rule sort of thing for getting it. But yeah, definitely there is a way. If I give you a regular expression, you can convert it into an equivalent DFA, and you will see that in the coming lectures. So, okay, but
Okay, ma'am.
okay, good. Okay, if there are no other questions, I think yeah, we can stop.
One doubt.
Yeah, sure.
If we want to construct a DFA where uh, it will only show, it will only consist of strings that are divisible by 4 in binary number,
Hmm.
then how we will draw that? Like sigma is 0, 1.
Okay. Um, okay. Sigma is 0, 1, and you want to
And
double.
language consists of strings that are only divisible by 4. Then how we will draw the DFA for this one?
Okay, so give me some time, please. Okay, I haven't thought of this offline, so I'll try to construct. You can also
Okay.
try if you want. Yeah.
Ma'am, can I give the answer?
Just give me 1 second, okay? Just give me 1 second. I'll ask you.
Okay.
Okay, so what is the sorry, what is the DFA that you have, Anisha?
I have drawn 4 states.
Okay.
In square, you can draw Q0, then Q1.
You mean table?
No, DFA Q0,
Hmm.
then
Q1.
Q1, Q2, and Q3.
Hmm.
Q0 to Q1,
Hmm.
0,
Okay.
1.
Okay.
Q1 to Q2, 0, 1.
Okay.
Q2 to Q3, 0, 1.
Okay.
And Q3 to Q0, 0, 1.
Okay.
And initial is acceptance.
Okay.
Yes, but in DFA, there like in DFA, only for one, it will be only one path. No?
Sorry,
What?
what
This
I'm
is
is
not.
it? Oh.
this is NFA, no?
No, this is DFA, right?
No, this is DFA.
In DFA, like for one there should be one path, and for zero there should be other path. No?
No, it is fine if you have. I mean, it is fine if 0 and 1 both go to the same state. But What is not okay is on 0 you go to say Q1 and also at Q2. Multiple transitions is not allowed. But you can still, 0 and 1 can still go to the same state.
Okay.
Like just in case, like if whenever you have doubt, just look at the definition of the transition function. So we defined it to be Q cross sigma to Q. What it says is, if you are at any state and you see any symbol, it should take you to some, sorry, yeah, it should take you to some state in Q. That is the only constraint. Anything is okay. So it is possible that Q0 on 0 takes you to Q1 and Q0 on 1 also takes you to Q1. So it doesn't violate any definition. So as long as it doesn't violate the definition, it's okay.
Okay.
Okay, good. So okay, so I'll check if this is the same language. You all of you who are in the call, you can also check if the answer is indeed it is the same language. So I think I have a counter example. Okay, so if you look at this string 1101, then the binary, the equivalent of this decimal equivalent of this binary number would be 1 plus 4 plus 8, which is 13. And 13 is not a multiple of 13 is not divisible by 4. So this should not be accepted. But what our DFA will do is, on 1 it goes here, on 1 it goes here, on 0 it goes here, and on 1 it goes to Q0. So it should not be accepting this string, but sorry. Yeah, this string, but it ends up accepting. So maybe there is some modifications that we may need to do.
Madam, what is the problem statement? The string should be divisible by 4, no?
4. Yeah, yeah.
It is only that?
Yes, yes. Not the string length, but the string, the value of the binary string.
Value of binary string.
Yes.
Okay. What I thought, the length of the
Length of,
string
okay.
is divisible by 4. So
Yeah.
I have designed the DFA for that problem statement.
Yeah. For that problem, this is a correct DFA.
Okay.
Yeah.
Okay.
Ma'am, I have one more.
Okay, sure.
Like I have taken 4 states.
Okay.
Q1, no, linearly.
A linear, okay. Sorry. Q1, Q2, Q3, Q4.
Uh, Q1 to Q2 1.
Okay.
Q1 to Q2 to Q3 1.
Hmm.
Q3 to Q4 1.
Hmm.
Then in the same fashion, like again, 4 to 3 it is 0. 3 to 2 is 0. 2 to 1 is 0. And on 1 it is self loop on 0.
Okay. And which is your final state? 0.
Q1.
Q1, correct. Okay. Let's see. So let's take same example 1101. Okay, sorry, this is not a complete 1101. Right, so okay. Okay, what about 107? Yeah. I think this is correct. So I think your idea is that you take this modulus, right? So if you
I
see,
take the it is representing a remainder, like remainder 1. I have taken it remainder 0, remainder 1, remainder 2, and remainder 3. If
correct.
it is remainder 3, then it will be it will go to 0, like.
Hmm. Yeah, I think that is correct. Uh, I don't see a counter example. Okay. Um, I think when I was trying to do using the same logic. So this so this corresponds to the remainder 0, this corresponds to 1, this corresponds to 2, and this corresponds to 3. And whenever you go on reading element, you keep adjusting your transitions accordingly. So I'm not completely sure because uh,
Ma'am,
because
can you
I
randomly take a number divided by 4 and check?
okay, let's try 100 and for anything here. Okay, so let's try 1 1 1. Sorry, where was the transition for Q4 on 1?
Q4 on.
Okay, what I'll do is I'll stop the recording so that it doesn't exceed. Then we can continue.